fourth Big Data Analytics class. If you look at the syllabus, you see that the first, I guess, first third of the course, we have a bit of room to do a bit of review on the key quantitative tools, probability, statistics, linear algebra, and calculus. But I believe most of you are pretty okay with at least calculus and maybe linear algebra. But what I'm going to do is the first half, maybe the first third of this class, is review the concept a little bit. Not so much because you don't know how to do the statistical modeling or calculus, but because I want to rephrase things in terms that would be in line with what we try to do with data analytics and machine learning in the second and third part of the course, right? So I guess maybe the first, I'll try to keep it to maybe half an hour, just run through the concept. So if we use this as a sort of like a check, right? So if I mention something that you're not familiar with or you've already forgotten, make a note of it. Then either come to me later, or you can, go to a tutor or your TA later, and just make sure that you have the firm understanding of the things that I mentioned. For those who have a solid understanding of how to do the calculation, then pay attention to the rephrasing, how I frame this as a data analytics tool rather than, say, statistical inference. Right. So that'd be the first half, the first bit of the class today. And the second bit of the class, I would then do the following. We are going to be studying data in most of the time. A lot of the tools that we'll be using in this course is based on machine learning. And as I mentioned from the very first class, right, we have supervised learning, unsupervised learning, reinforcement learning. This class will not cover reinforcement learning. We'll cover quite a bit of supervised and unsupervised learning. So from next week onward, we'll start to visit or start to go into the supervised and unsupervised learning. Now, what we can do is to actually just take some toy data, right? Like example data from Mathematica's repertoire or the repository or some data set. But for unsupervised learning, what I want to do is actually create artificial data. Okay, create artificial data set. Why do I want to do that? You'll see that by creating our own data set, we can kind of like pretend what the reality looks like and see if our analytics, our machine learning does get the right answer, right? So instead of getting it, because if you get the real data, right, ultimately it is empirical. But if we generate from scratch, and we can use random variate function to do that, we know what the correct answer is, right? And then we can give the computer algorithm, okay, whether or not we're talking about supervised learning or unsupervised learning, let it try to come up with the right solution. But you know the right solution because you created it yourself. So that's the second part of this class, is that, okay? And even though I'm going to be creating the tools, what I want you to do is go along. As I go along, just open up your own Mathematica and just key along from scratch as if you were, doing this with me. And good thing about me being forgetful is that even though I've used a lot of functions, hundreds of times, I still keep forgetting the syntax. So I would probably have to go to the help page to see what the syntax is. And that would be exactly how you would have to do it for the first time, right? You want to do this plot, you're not sure, how to use the syntax, or what you call first, the range, the value, so it's going to be very close mimicry of you trying to program for the first time, maybe. Okay. Right. With that, I'm going to walk over there. Let me do the voice check. Can you hear me okay? I can unmute here. Nope. Let me try to mute here. Yep. Okay, let me try to mute myself here. How about this? Oh, that's not good. It out, but we have one of those microphone that would be nice, but okay. Let's make the best. This guy. That's as far as we go. Okay. Right. Okay. So what is okay? Okay. Today I'll just make sure that we walk through the concept and see that you understand you're on the same page as me. Okay. So first thing first, in linear algebra, this is all I want you to feel comfortable. Yeah. Okay, you guys know this, right? It's a matrix. Yeah. Right. So this is M by N, right? This is M by 1, correct? Yeah. And that represents say x1, xm, right? This is A11 to K1n, K1, right? So as you multiply this by that, you get scalar, correct? As you multiply the second row by the same vector, you get the second guy, right? Yeah. So, okay. So what it does is say x is a vector now is equal to g. Yeah. Now, what's the dimension of b? B is n by 1. B is n by 1. X is n by 1. This is a general system of equations. But for most of the time, we're going to restrict ourselves to square matrix, which means that this is also n. Square matrix, right? So why is the square matrix? By the way, the square matrix is so ubiquitous that sometimes if you don't have a square matrix, you would pad it up to get a square matrix. Okay. But okay, let me stop here and just erase this and say, okay, here's the key concept you need to know. A is a square, x, right? Now, this represents a system of equations, and it has as many unknowns as there are equations. Okay? If you were a kid, you were saying something like, 2 equations and 2 unknowns will be the answer. Okay? What matrix algebra essentially does is to qualify first that this is not always the case. Okay? I'm showing why. Now, first of all, think of this. This is a matrix equation. Matrix, square matrix, vector, right? And think of a simple equation like say 3a is equal to 7. Right? So that's an analysis. Here's the deal. In this case, we know that a has an answer. Okay, a is equal to 7 divided by 3, right? Yeah. Very good. Yeah, this is my elephant catching the little cricket. Yeah. A is equal to 7 plus 3. Okay. I want you to slow the step down a little. This is in one shot, right? I want you to say, no, I don't want you to do. I don't want to do. I want to find some guy. Okay. I want to find some guy that multiplies to 3 and gets to 1. Okay. I want to find somebody that multiplies to 3 and nullifies the thing. Okay. So, yeah. Right. So I can do this. I can just put 3 in the bottom and I'm done. But I don't want. I want to stretch this process out. I want to say, hey, I multiply 3 by 8 and get 7. I want to find something that multiplies by 3 and undoes the multiplication. In other words, becomes 1, right? Because 1 has a is nothing. Okay. So what does undo the effect of multiplication by 3? 1/3. This thing is 1/3. Now I multiply the undoing on both sides. Again, numerically 7/3, right? Simple as that, right? But this is a step you take. Yeah, you find something that's kind of like an antidote to 3. Okay. So in this case, I can write it this way, or sometimes I can write it like this: 3 minus 1, right? 3 to the minus 1. So 3 to the minus 1 is the multiplicative inverse of 3. Correct? Okay. That is a step that takes a long time, right? But simple 3x is equal to 7. You don't want to do that. That takes forever, too much. But instead of having that, what if you have this? Okay? And instead of having 3 equations, 3 unknown, you have 10,000 equations in 10,000. Now it's kind of worth it, right? Now it's kind of worth it. So matrix algebra, the reason that you do all kinds of matrix theory, it's motivated by what you wanted to do, right? Just find a solution. AX is equal to B. But you want to do it for an industrial scale. Again, I'm trying to replace everything you learned. And this is, was about big data, right? So this is not 5 by 5 or 100 by 100. It could be 10,000 by 10,000. Okay. The project that I'm doing right now has a matrix size of 40,000 by 40,000. Okay. Now I'm not trying to find the inverse, but that's the thing. So I'm going to write this in a matrix form. AX equal to B. Bear in mind that B is a vector, X is a vector, A is a matrix, a square matrix. It's 40,000 by 40,000. Right? So what I want to do, I would love to do X is equal to B divided by A. But I can't do that. That's not possible. So what I try to do is in analogous to what we did before, find something that inverses the effect of A. Okay, and multiply to this side. What do I mean by inverse? When I multiply it, I get identity matrix, identity matrix, right? 1 in the middle, in the diagonal. Okay, so this is all maybe 60% of matrix theory. Okay, this is a 60%, 70%. You're trying to find this guy. Okay, so it's so if AX is equal to B, a system of equation multiplication on industrial strength scale, 40,000 equations to 40,000. This is about finding the solution by finding the inverse of that, so that you get the solution. Okay, so we're on the same page, right? So the first thing you have to know is, have a matrix. Chances are you probably need to find the inverse. Okay, so that's number 1. Take that home. What else do you take home? This is what you take home. Each equation draws a linear relationship. I'm going to go back to 2 by 2. Baby step. Baby. Okay. 2 equations, 2 unknown. Who get the solution? That's what you learn when you work with equations. No, that's not true. It would get to the solution under certain circumstances. Okay. So if I draw this on a plot, ax1 plus bx2 equals to y1. I get a linear equation. So I get a line. Right? I get a line. Okay? I get c x1 plus bx2 equal to y2. I get another line. And they cross. What happens now? This is the solution. So yes, in grade school, you will always get this situation. Okay? And how would you do it? You would find the inverse of this. Essentially, when you do the substitution, it's the same thing as finding the inverse. But yeah, the importance here is that your grade school teacher didn't tell you everything. Okay? In life, there are 3 situations. 3 situations in life. Okay? This is one situation. There is only one solution. You must do it. No option. Okay? Doable must be done. No option. That's called unique solution. I'll give you another 2 situations. Yeah. What if I get 2 lines? They are parallel. Get no solution. This is infeasible. This is also life. Yeah, this is also life. By the way, you're going to get into the line of atomic business. Get used to negotiation, because chances are when you walk in there, that's the situation. Yeah, that's it. Okay, so then 2 lines. Okay, but they don't meet. So you then get no solution. Okay, let's go to another situation. Okay, another solution. I get 2 lines, but it's exactly on top of one another. What happens? Do you get a solution? No, you get infinite. So matrix algebra, we try to find the inverse to find the unique solution. Now I told you in real life, you can't always do that, because there is a situation where, yeah, let's make this like a unique solution. We're done. Okay, and then there's 2 solutions where no or infinitely many solutions. Okay. Now I didn't make it 3 lines, I make it 2. Okay, there's one junction here, there's one junction here. Here's why I did it that way. Why do you think I did it? Because these situations are very close to one another. Why are they close to one another? Because the 2 lines have the same. Right? So in other words, if I get this, either this equation here, gives you 1 line, and this bottom equation gives you another line. So that's unique solution. We're done. Okay, this is your grade school. The grade school. The teacher will always give you this. The other situation is either infinitely many solution or 0 solution. It turns out that these two are similar because what it means is that the left-hand side gives the same. But it depends on whether the right-hand side also plays along. If I'm going to make another case, let's say C is equal to A. Simple as that, right? C is equal to A. D is equal to B. Okay, so it's actually same number top and bottom. If the right-hand side plays along, that means y2 is equal to y1. Same line. So you're a fool. You pay for two equations when you only got one equation. The other one is just a copy. So that's this situation where it's on top of each other. The other situation is C is equal to A, D is equal to B, but y2 is not equal to y1. What happened? That means it's a contradiction. Zero solution. Okay. So instead of saying that you will try to find A and then you find A inverse, there's an intermediate step here that professional mathematicians and computer scientists do, which is ask, does this even exist? Is it doable? It's doable. Now, go back to the simple baby equation I was telling you earlier. If I have something like 3x, 3a equals 7, right? I can find the inverse, right? The situation there where it's impossible to 0a equals to right-hand side. If 0a equals to 0, infinitely many solutions. Everything multiplied by 0. If 0 times a equal to 5, no situation, because the left-hand side is 0, the right-hand side is not 0. It's a conflict. Now, this is probably not a fair question. What do you think is your situation in life? What's the most common? Well, I can tell you that, from consulting experience, chances are you walk in day one, that's your situation. You get into too many requirements. Your clients want everything. That's not the rule. Yeah. You would think, because you grew up in grade school, that unique solution is the common choice in life. No. In life, this is the most common. What you do is you establish that it's possible, something is possible, but there are many solutions. In fact, there will be more than one or infinitely many solutions. Then from here, you take it to the next step and you find optimality. Yeah? And optimality is the second anchor of a finite intelligence. In a finite intelligence, if you talk about the software analytics part, right? If you talk about hardware like robotics, that's something else. But even though software analysis, mathematical modeling, there are two anchors. One is the analysis of data. The other one is the optimization. Okay. This optimization is basically your life. You are paid, consultants paid to start from something that's impossible, take it somewhere it is possible. But hopefully, not only is it possible, there are choices. And then you take the best. Okay? So this is why you want to check whether or not the solution exists. Now, I gave you a simple example, right? Where C is equal to A and B is equal to B. But the only thing you find is what? In order for the two lines to have the same slope, what it means is that A to B is the same thing as C. Right? Okay, now that's the situation where we have trouble. Okay, so problem becomes, so if this is A, okay, if A does not exist, exists not. If A to B is equal to B, okay. Alternatively, I'm going to switch this around. A, B minus B, C. Okay. In matrix theory, if this is your matrix, this is known as the determinant of the matrix. It determines whether or not you are in trouble. Okay? So this is written as like the size of A. It's almost like the size of A. Okay. Also, it's written like this. Now, remember this picture because in my problem, like I told you, my matrix is 40,000 by 40,000. This determinant will be a big calculation, but it is a finite calculation. Yeah. Once you understand that, once you understand this, just trust me that in higher dimension, you get the same thing, but a lot messier. Okay, a lot messier. Okay. So, for example, okay, let's say I have file new. Okay, and oh, I have to erase that thing. Remember, we can make an array, right? Let's say my A is equal to array of A of size 4 by 4. Okay. In fact, let's look what matrix form look like. It looks like this, right? Okay. So instead of having just A, B, C, D, where I know that to get the same information in this cross multiplication, now I would have to use determinant function. So determinant I don't know what the determinant function is called. So let's find out. DET. DET of A. That's DET of A. Okay. So it's obviously messier, right? It's obvious. You don't have to worry about it. All you have to do is understand the concept behind it. Okay. So assuming you understand the concept behind it, what you need from matrix theory, okay, is first of all the mechanical multiplication. So I would say this: you have to be comfortable with a few things. You see this and you see this, you can multiply them. Dot product, okay, you have yeah. Let's just split them. You need to be able to do this. That's called dot product. You need to know that this thing multiplied by this thing equals to this thing, and you want to deal with this. You need to know that this thing, you want to find the inverse of that. The inverse doesn't exist if determinant of this thing is equal to 0. Okay? All this you have to be comfortable with, otherwise we can't move on. Okay? But again, if this is it's 4 by 4, you have to do by hand. But none of it will have to be done by hand. Okay, but conceptually you have to understand. Okay. Now, in this case, right? I'm going to go back to this. What it does is that when you get x and you get y, x and y is the same dimension. What it means is that you transform x into y. That's the word. Okay, you don't say multiplication by matrix. It's called linear transformation. The reason it's called linear transformation is because you are transforming x's into y. Now, if x's were 2 dimensions, it's on the plane. If x is in the 3 dimension, it is where you are. So imagine that this is x, y, and z coordinates. And this is 0. I can go x, y, and z end up with a. Okay? So your head is a vector from 0. I multiply your head by a 3 by 3 matrix. What's going to happen is that you are going to rotate. And this arrow from 0 to your head may lengthen or shorten. Maybe let's say it's here. Okay? Okay, make here. Shorter and in a different direction. Tell you what, the action of this is equal to this thing. Okay? This thing is some kind of action that rotates. And then there's a multiplication factor that lengthens or shortens. That's the and that's why it's written like that. Because it looks like the size of a vector. This is the size of a matrix. Except a matrix is not an object, it's a transformation, right? In this case, so it is the size of the transformation. So if I have an arrow from here to where your head is, and I move it so many degrees to the left, and I lengthen it by twice, what is the determinant of that matrix? Right? What if I take an arrow from here to the head, multiply by a matrix, and it actually goes to the root? It's just right to the opposite side. It's minus. Right? So it doesn't move. Now, so this is very important. But why is it important? Right? It's important to the story. Computer graphics is based on that. Computer 3D graphic, gaming, you know the gaming, right? I have to say action, right? So it has to move in there. That's all matrix multiplication. Yeah. It turns out in machine learning, you are also going to have a lot of matrix multiplication. Make the long story short, the breakthrough in deep learning that you are beneficiary of today, you have to thank two people. You have to thank the mathematician who comes up with the model, and you have to thank gamers. Because gamers play a lot of games. So they created this thing called GPU, graphical processing unit, that does nothing in life. Its whole purpose in life is to multiply matrix. Because of the gaming boom in the late 90s, NVIDIA developed graphical processing unit so that it multiplies matrix so fast, so quickly. Okay? Do inverse, all kind of stuff. Okay? So fast, so quickly. So that people like me who studied neural network also needed that, but we couldn't do it before. We had the mathematics. The mathematics that we have today was around in the 70s. Okay? This detecting cats and everything, all kind of stuff. Convolutional neural network. This has been invented since the late 70s by a Japanese neuroscience researcher. That's Fukushima. Like Fukushima out there. Anyway, he invented it. He couldn't do anything. But no, I'm making a story. Okay, but the biology that was discovered in 1958 inspired Professor Fukushima to come up with neocognition, which is like convolutional neural network. But if you were to do convolutional neural network in the 70s, it would take him maybe half a year of computers, draining the electricity. So maybe that's why he didn't keep a power plant. But because of the NVIDIA part was so efficient at multiplying matrix, somebody took essentially something similar to Professor Fukushima's model, used the game card and came up with what's called Alex. So this is kind of first generation of this. Okay, and that, if I understand properly, if I remember properly, I think it took 16 hours or 16 days. I seem to remember number 16 and number 5. Maybe 5 hours or 5 days, something like that, to calculate. Now it will take you a millisecond. The point is, before the gaming boom, we couldn't even do that. Before the gaming boom, I was there. I was studying neural networks in the 80s. Well, not 89, but not that. I was studying neural network in the late 90s. Yeah, it's not something doable. It's not something doable with a CPU. No matter how expensive it was, CPU couldn't happen. And then, NVIDIA, so around 2000, 2005-ish or something, game card became available. 2011, very smart guy. By then, I was no longer working with the neural network. Use that, NVIDIA, the rest of it. So all you need to know is that there's a lot of matrix multiplication in the back of everything else we're going to rely on in the life. In terms of deep learning. Okay. Now, before I go to that, there's one more. Again, this is something that's not covered in, say, linear algebra 101, but I'm choosing to cover it because it's going to be so useful in your life. Just now, I was telling you that, okay, we're working with square matrix, so you're not changing dimension. Okay, it's 3 dimensions to 3 dimensions, but different place and different length, different distance from the point. It turns out that if you're in 3 dimensions, right? And I give you a matrix transformation. So this is 3 by 3. Right? I multiply this thing to your head and up here. Your head, I multiply by this matrix, it's up there. Yeah, it's sort of unbelievable. It turns out there is a sweet spot. Let's say your head. Your head is so perfectly suitable for this matrix that when I multiply this matrix to your head, the result is exactly the same direction. Okay? The result is the same direction. What's the word for same in German? Any German speaking? Eigen. Eigen means same. So if I multiply this, and all I do is make it longer or shorter or negative. By number. Yeah. So this is 3 by 3 matrix. This is the vector. This is the vector. This is number 7 minus 2. Exact same vector. The same in German with eigen. This is called eigen vector. Eigenvector. And this is called eigenvalue. Okay? But the cool thing is eigenvector. There are 3 of these in 3 dimensions. Yeah. The object here is not to find the solution ax equal to b, find x. The solution here is actually to find the x that happens. Right? So different from the earlier question, right? Earlier question have a x equal to b. Find x then multiply by a equal to b. In this case, I give you just a. I don't give you the right hand side. Find me an x then multiply by a and still get at the right hand side x times a number. It's a different problem. Yeah, it's a different problem. This problem is called eigenvalue decomposition. Okay. Why is it so important? Well, it gives you the sweet spot. Okay. Eigenvector system decomposition says that when you try to transform the system, you just multiply, magnify, okay, or oscillate, right? If you go from plus to minus and then plus to minus and plus to minus, you see the same direction. Okay. Eigenvector decomposition is so important in so many systems. In engineering, it's one of the most important concepts. In economics, it's one of the most important concepts. Eigenvector decomposition, that's what the Bank of Thailand uses. And this is also one of the most useful things in data science. Because you are kind of like summarizing the action of this by finding the sweet spot. Okay. Now, technically, how do you do that? Well, you say equal to this. Okay, that's how you do it. And I put in the middle, identity matrix. Identity matrix, right? Nothing. I can always take identity matrix into that, like, correct? So I turn AX equal to lambda x And then, by the way, once you go to eigenvector, they don't use X and use U. Just to sort of like highlight the fact that it's so special. Okay. So what you want to do is this: A is a matrix, mu is a vector, and it's equal to lambda. That's the number, and that's the U. That's what you want to do. So again, this is eigenvector. This is eigenvector. So what you want to do is stick independent identity over here, right? And you put lambda over here, lambda. Okay. So it becomes A mu equal to lambda identity mu. Right? So this becomes A minus lambda identity equal to mu. Right? Okay. Sorry. Becomes A minus lambda identity mu equal to 0. Okay? Right? Now, in order for this to work, go back to the beginning of the class. What has to happen? To get no contradiction. You can only get something to be 0 if you multiply by 0. So if this thing is not going to be 0, this thing better be 0, in a sense, right? And that means the way they find it, you have to pay attention to this so much. What they do is they say determinant of this guy has to be 0. And let's just go back to earlier when we talked about. So basically, it has to shrink 0. What it means is that this is a sweet spot. When I multiply U by matrix, I still get U, meaning also short. So that if I take the action of the matrix minus the action of that multiplication factor, it must reduce to 0. Now we find, so basically that's the third thing. So this is basically you solve it. Now, technically again, like in my project I'm doing right now this week, by 40,000 by 40,000, you're not going to do it by hand. You're never going to do it by hand. The point is, once you find this, you can get the income now. Okay? Why is it important? Okay? How's that going to make money? Shut down the thesis. Because you always want to make money, right? When I was your age, well, I'm a little older, I'm starting my PhD. When I was your age, we have a proposal, social motivation. Then when I was starting to do my PhD, started to write up, I have to look for underpaid and whatnot. So the search engine I was using was called AlphaVista. Anybody today use AlphaVista? No. Why do you use Google? Because Google kills everybody. How did Google kill everybody?
Because search is over.
The search is better. Why is the search better?
Because
they have the algorithm. Okay. To make a long story short, I'll tell you later. The reason that Google beat everybody was because there's a matrix that Google accumulated. And then Google found everything. Okay? The reason the page are ranked or page rank, that's nothing. Page rank, you read the paper, page rank ranks pages according to eigenvector of the matrix that I am doing now. So there's a matrix that represents how internet pages link to one another. Google has it because Google is the one that gives the link, right? Solve this mathematically, and then links the page with the highest value in this. So let's say get this eigenvector of 1,000 pages. Okay, 1,000 pages, and this thing is 0.1, 0.2, and this one is 0.7, 0.3, 0.2. What Google did was to take the page, this page on top, followed by this page, followed by this page, followed by that page. And that's how Google beat AlphaVista and there were a few other search engines in the late 90s. So PageRank was eigenvalue decomposition of the adjacency matrix corresponding to page numbers. Okay, so yeah, it did make money. Yeah. Now, from your perspective, there is going to be a situation where the data is kind of spread everywhere. Okay. Now I'm going to do hand waving. I'm going to do nothing more than a hand waving. Just like there's a speed direction. Good direction is the speed direction for this matrix. Okay. So when I multiply by this, it only has goes higher or shorter, or it goes negative, but it doesn't change. It likes this direction. It likes this direction. Now imagine that in the distribution of data goes in all kinds of directions. But there's also a speed direction. That speed direction corresponds to the direction where you get the highest variability. Yeah. In this row, what is that direction? Come on. Are you guys up and down all over the place? No, you're actually on the same plane, right? So obviously, there's that direction, Z direction. There's no variation. Are you kind of up here? No, you're actually in the back of the group. But there's one line actually. There's the one line that draws like this. From this point here down to that point. That line has the greatest spread among you guys. Stretches the other one. To find that line, you solve eigenvector. Okay. In fact, there are three lines. There's one line here, one line here, this line from the border. So, just as in engineering, you need to know about things like resonance, system response, same like in economics. Macroeconomics is nothing but system response. I-O. Yeah. If you take this with this direction, it goes in the same direction. That's an eigenvector of an economic system. Yeah. If I multiply your head by this vector and keep going here, that's a sweet spot. If I look at the data spread and there's a longest direction of variability, that's a sweet direction. That's why eigenvector decomposition becomes so important. It's usually there's so many decomposition theorem in the matrix algebra. When I was studying matrix algebra, I learned about 3-4 of them. But in life, I only come back and see one of them all the time. That's eigenvector decomposition. Singular value decomposition? No, never will happen in life. Even though that's actually the first one I learned. So there may be 3 or 4, and I'm just kind of like hand-picking them for you. Because I know from life experience that if you're going to know one decomposition theorem in matrix theory, eigenvector decomposition will okay with 1,000. Okay? Yeah, I can confidently say that I have never used single value SPD decomposition. I've used lower upper triangular a few times in finance. Again, I'm from like finance economic background, so a lot of things I see from that perspective. But definitely, I can think of it. So get comfortable with that. I'm going to move on. Okay, so that's a march on the topic of linear algebra. Okay, know how to do this? Inverse, determinant, get familiar with all those concepts. You don't have to do it by hand. You use Mathematica for that. Fine. But you have to understand what you're doing. Okay. Let's go to calculus. Calculus. Very important. I told you from class 1, right? At the end of the day, all we're trying to do is model. Okay? What do I mean by model? You give me some information, I give you the conclusion. Give me X, I give you Y. Okay? Now, the sort of information that you ask can be given to me as a question. If you can give me X, I can give you Y. You ask, what if tomorrow's X were like this? What will be tomorrow's Y? Then that becomes predictable. Yeah? So at the end of the day, this is the input, response or output. In linear algebra or matrix theory, you deal with multiplication on an industrial scale, like I said, 40,000 variables. But the relationship is linear. In other words, it's kind of like in 3 dimensions, it's a plane. Okay? So, if I were to do this, I can do certain things by multiplication, right? If this is my speed, this is my time, distance. Okay. So this is my time. This is my distance. Yeah. Actually, let me use S for distance. Yeah. Doesn't make it obvious, but right. Yeah. And I have this. That's a train, right? So it starts here in Bangkok. 2 hours later, it ends up in Odin or something, right? Right? How do you multiply things? How do you multiply? Well, distance times time equal to, speed times time equal to distance. Okay? So distance equals speed times time. Okay? Speed equal to distance divided by time. That's it. If this function is linear, that's all you need to know. But if this function is like this, okay, how do I know? Okay, here, what's the speed, by the way? What's the speed? This divided by this, right? Right? Well, what's the speed here? Well, overall, you can do that. But you notice that it's not instantaneous. So the whole idea is find instantaneous. So the only thing calculus allows you to do is try to find instantaneous. So that you don't have, you can do this kind of height divided by width. You can find it slow anywhere. Here, instantaneously. That's it. That's called differential calculus. Integral calculus is the reverse. It's the multiplication. If this is differential calculus, this is integral calculus. You try to multiply, but normally what you do, you multiply height by width, right? But what's the height? Height changes all the time. So you have to have instantaneous height times width. That's integral calculus. Okay? Again, with Mathematica, you can do this analytically. I told you that before, right? Let me give you an example. And again, I apologize that my example is always something to do with finance and economics because that's my career. Okay? But anyway, so you got something, price of something, Thai baht, I don't care. Okay? Then you have a price of something else that moves functionally linked to this. Okay? The reason, this is something I want, I don't know if you know anything about risk management. Risk management means in finance, you prefer things to stay calm. It's the opposite of Hollywood, right? In Hollywood, if you go to a movie and nothing happens, it's boring. In finance, you want boring. Okay? So, if this is the excitement of investment, this is also excitement of derivative investment. In finance, they want no excitement. They want this guy to cancel with that guy. Okay? Some of you may have a friend in finance department. Okay, so what you want to do is find combination of this. So obviously, what you want to do, if this thing moves up and if this thing goes down, in what proportion? You can create a combination, right? Right? That's called risk management. So the risk management is to find change in this and change in that instantaneously. So instead of distance over time, this change in derivative, given change in stock price. Okay. Anyway, so that's really told that we might actually have some I think either finance or economic students. I don't know if you know anything about it. So the deal is in calculus, that's what you want to do. Okay? Allows you to basically multiply by and find the ratio of it. Okay? So that you can make this kind of proportionality. Proportionally change in X, proportionally change in Y, but do it instantaneously, not just over and on along the average. Yeah? Now, why does that matter to you? Because remember I told you that in life, what's the most often what's the most common situation in life? Infinitely many solutions. You are doing regression. Okay? Draw me a linear regression line. Is this a valid linear regression line? Yes. It's no good. It's valid. It does its job, right? You give me an X, I'll give you a Y. It does its job. It does its job poorly. This one does a better job. This one does a better job. Okay. So, if the coefficient of the slope corresponds to how good a job, what do you want to do? Change in error by change in slope. And calculus comes in here. Calculus say, I'm going to keep changing the slope until I can't change error anymore because the error is the lowest I can get. Right? So this becomes the basis of error minimization in all machine learning algorithms. So I don't care what machine learning algorithm you have. It could be linear regression all the way to deep learning. Underneath it, it's going to be some algorithm that changes the bottom here to make the top go away. And that will always be a calculus function. So calculus will come no matter what. Calculus will come no matter what. Now, integral calculus doesn't play so much a role here, but definitely differential calculus. So I've walked you through linear algebra with the emphasis on eigenvector decomposition. I've walked you through calculus with emphasis on differential, right? Because in a way, it's going to be all the algorithms, all the machine learning algorithms that you will ever play with for the rest of your life will have somewhere in the step something like this, something like this. And then you keep tweaking this until this thing goes down to that 1%. Okay, so that will always be a differential term in your thing. Okay. Calculus. Now, two more things, and then we'll cover the first part. Probability and statistics. Okay, again, this is not meant to be a review. It's to check the understanding that we are A, on the same page. If not, make a note. B, even if you understand this, if you've done this 1,000 times, I'm going to recast everything in the term that is in line with what we do in DataAnalytics. Okay. So, probability and statistics. Yeah. Okay. Probability. I'm going to claim. Probability is all about creating a model. Except this conclusion of the model is not, is it going to rain tomorrow? The conclusion will always be a probability. Yeah. That doesn't mean that I can't answer you the question about is it going to rain tomorrow. I just have to make it into a probabilistic statement. I can't say, is it going to rain tomorrow? That's not a probabilistic statement. But if I ask you, what's the probability it's going to rain tomorrow? Now it's okay, right? Talk about probability. So I say, I give you a probability of 0.3 it's going to rain tomorrow. Okay? So that means that, if you, this quality of test, you can kind of like, you're fairly sure that it's probably not going to rain. It's less than 50, but it's not that much less than 50. You can't do much with it. Okay? But at the end of the day, it's a probabilistic. A probabilistic statement created from mathematical. So a mathematical model, remember, y is equal to f of x. This is a mathematical model. Okay. Probabilistic model is saying something like probability P is some kind of function of information. Okay. So everything that you learn about probability, about mean, variance, standard deviation, normal distribution, blah, 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 blah. I want you to rethink that and say that at the end of the day, I want to get probability as a function of information. Most of the time, that information comes from the probability. Most of the time. Okay. So y is a function of x. I don't want y, I want p. It's some kind of function. In fact, I might as well call this function p function. Okay? And information. Okay. Now, I'm going to break this down. What's the probability of some event? Probability of some event. Again, we talk about it's going to rain tomorrow. That means the probability is 1. What exactly can you do to turn every single statement on Earth into probabilistic statement? First, you have to establish possibility. Okay. Because probably, what's the probability it's going to rain in this room tomorrow? It's 0. It's not going to rain tomorrow in this room. Okay, it's never going to rain in this room. Anyway, establish possibility. Establish. Well, I'm just going to use the word probability again. Use the word likelihood. It's a probability function over range that you specify, and then range that you specify. 3 things. Again, it has to be able to rain tomorrow. Otherwise, you can't talk about rain in a probabilistic term. Yeah. Also, if it's certain, there's no point. Yeah. Number 2, there's a probability function. That probability function is going to give you a number between 0 and 100%. Yeah. Can't be 150% sure of anything. Yeah. That probability function is going to cover something, saying rain in the future. But in order to do this, I specify not just any time in the future, I'm going to say tomorrow. So that means something like 0, 0, 0 to 24, 0. That's it. Okay. Remember, there are 3 things we have to make. We have to have possibility, probability, and the rate that you are asking about. Because if you don't have specify the rate, what is the probability it's going to rain in the future? Anybody? For sure, it's going to rain in the future. Makes no sense, right? So, get the path to get in this room. It has to be in the future. But if I say, what's the probability it's going to rain in the future? It also makes no sense. So I have to narrow down the rate that I inquire about. I inquire about this tomorrow, or maybe tomorrow between 3 and 5. So let's turn that to the usual distribution function that we see. Yeah. How can we make this a probability statement? Anybody? Now look, very important that you look here. What's the possibility here? Anybody? Minus infinity to plus infinity. What's the probability over any range? That's this turtleneck, this Napoleon hat. How can I turn this into a probability number? I have to specify, right, between A and B. Now I can say this is a number between 0 and 1. Okay, so that becomes a probabilistic statement. A probabilistic statement has 3 elements: possibility, probability function, that's where mathematics really pays for itself, and then, well, your question. Your question can be this A and this B, or it could be this A and that B, right? Or if you want to be silly about it, A from minus infinity to B plus infinity, in which case, totally take 1 anyway, right? But that's not interesting. So all probabilistic model has to do with you establish 3 things: possibility, forever, probability as a function of the mathematics, and then the question. Now, what can change? Now, it's very important. What can change? The possibility cannot change. Like if I talk about rain, it has to be in the future, not in the past. Okay? Possibility cannot change. What about probability? Well, this way it gets tricky. Technically, it doesn't change, but your understanding of it changes. So this line, in reality, if you want to be able to, if you have a direct line with God, okay? If you have a direct line with God, you ask him what this line is. He told you, and you write that down. Yeah? But, so that doesn't change, But because you don't have the direct line with God, you have to estimate from data. Based on your data, maybe you draw this line. If you get a different set of data, maybe you draw a different set of lines. So it changes as a function of it. And so will your conclusion. That's what probability modeling. Yeah, probability modeling. Now, what is the job of a mathematician? Job of a mathematician is to give you a function that somehow non-negative, and the area under from minus infinity to plus infinity is 1. That's the job of mathematician. And the mathematician is nice. He doesn't just give you 1 line, he gives you a style. It looks like this, but it could be here, it could be here, it could be here, it could be here, depending on parameter. Yeah. So what's the math? So probability distribution function is always probability distribution function. will always have parameters that you can tweak. Okay? So probability is about making everything probabilistic statement. That probabilistic statement will give you a number between 0 and 1. That depends on the assumption of the mathematics that you get. The job of the mathematician is to give you a whole bunch of different curves that looks kind of nice, the area underneath the 1, and but you can move it around, tighten it. It's up to you. You can squeeze it however you like, and you get different answers. And that's constructive thing. You are just imagining. In fact, if I have nothing better to do in life, I can just dedicate the rest of my life coming up with another function. A mathematician over the last 300 years has come up with thousands of functions. Okay? You can't find it in Mathematica, you can't find it anywhere, because it has a large library, it has larger library than R. and R was much larger than Python. So that's what you do. Try to find a function. So it's always going to look like this. By the way. Now I'm going to give you generic f. Okay, actually I can use p. But it's always like this. F of x given. This is how I'm going to write it. Okay, I'm going to write like this from now on. Okay, every time you see this, okay, this is x. This is some kind of function that has some kind of distribution. Okay, all I know is that the area underneath possibility is 100%. And this data allows you to shift, modify, sometimes drastically. Let's see how drastic it can be. Okay. Let's see how drastic it can be. Let's say I want to do this. Oh, I have to erase this, right? Okay, now use your hand or use your. Let's do the same thing as we do in here, right? So, file new. Okay. Okay, watch the screen. Plot, right? Now I'm gonna plot something. I'm gonna plot PDF. Now that mathematic function depends on mathematician coming up. So let's say I'm gonna use this one called beta distribution. Okay, and that beta distribution happens to have two parameters. Now let's say I don't know what it is. There's alpha and beta. Okay. Oh, I don't have to do it here. Actually, it's already there. Okay. Plot PDF beta distribution. Blah blah blah. See, the name of the function is called beta distribution. Okay. So this is the name of the function. This is what mathematician came up with. Mathematician came up with function. It gives you two parameters, two knobs, alpha and beta, two knobs. Okay. And the only requirement is that the possibility here is between 0 and 1. So in this case, it's not from minus infinity to plus infinity. It is between 0 and 1. Mathematician has to come up with a function that is positive between 0 and 1. The area underneath is 1 and has a parameter that allows you to tweak the shape. So this is basically the shape. Right? So this is alpha. Beta. Beta is 1.5. In this case, just mixing one. Okay. I keep beta to 1.5. Alpha, I can make it 1/2, 2, and 4. Look at how drastic the shape. This is one. This is another. This is another. And they're actually the same function. Okay. It's actually the same function. And that function looks like this. Okay. Now, we happen to use another thing underneath called beta. Let's look at this. It's 1 minus x to the minus 1 plus beta, and then x to the minus 1 plus alpha. And depending on how you change alpha and beta, depending on how you change this thing. In this case, this beta is 1.5. So put 1.5 over here. Then alpha, you can have 1/2, 2, 4. Let's put 1/2, 2, and 4 here, and we get the mathematicians have done that. Yeah. So that's the end of probability. Well, not quite. This is probability of one random. There's also possibility of 2 at the same time. And we talked about this thing where that's correlation of what. So it's univariate versus multivariate distribution function. And then there's some more detail, more hair splitting. It can be what? Discrete can be continuous, right? The possibility can happen over the range, or possibility can happen over discrete numbers. For example, amount of rainfall, that's continuous, right? It can be 0 inches to maybe 50 inches continuously, right? What about shower? Well, that's not continuous, which generally have 1, 2, 3, 4 showers, right? So what's the probability that Thailand would have 0 more person tomorrow, 1 more person tomorrow, but not 1.5? Having said that, when the number is big, sometimes it's a number of times. That's why you hear this joke where this country has a birth rate of 1.7 persons every week. This guy is the 0.7. That's this joke. Okay, so that's probability. That's probability. Okay. Now, I ask you, what is probability good for? It's good for making prediction. Good for making prediction. Prediction in terms of probability. But how good is it? How good is your prediction? Well, it depends on what? Anybody? It depends exactly on. So you have to choose the right function and then tweak the alpha and beta in the right way. Okay, 2 steps, by the way, 2 steps. Okay, 2 steps. Choose the name of your probability function. In this case, I chose beta. I chose y. But even though I chose beta, okay, there's nothing specific about this. So I ask you, what's the probability? It could be something like this big area or tiny area. It depends on alpha and beta. So choosing the right probability function is not even half the job. It's barely 10%. The job's not done. The job is, well, is it going to make sense? It depends on the alpha and beta. So what mathematicians give you, if you can tell me the possibility, if the possibility is continuous or minus infinity, plus infinity, mathematicians say, may I give you this menu of probability function? You ask, I want something that's non-negative but continuous. Mathematician will show you a different menu of probability. If you say, I want something that's continuous between left end and right end, let's go to infinity. Okay? Scale down to 0, 1, basically. Mathematicians will also give you another menu of possibility. Okay? So, how do I find out what they are? Well, sometimes it's good to go outside to the world and go to Wikipedia. Okay? I just go to any case. Okay, I happen to go to this normal distribution. This is one function that mathematician kindly gave to you. That mathematician, his name is Gauss. So he's German. I don't know how to pronounce it. Gauss. How do you pronounce Gauss in German? It's Gauss, right? Yeah, it's nothing deep. Okay, nothing tricky. Okay, here it is. This is a little bit technical word, but remember I asked you that it can be continuous, it can be discrete, it can be, so this is kind of like the possibility set. Finite support means it can't run away to infinity. With infinite support, it can go to infinity. Bounded interval means finite from the left to the right, like 0 and 1 or A and B. Semi-infinite, that means that you start from 0, go to infinity. Whole real line, minus infinity, plus infinity. So this is your job. The first thing is you have to know what you're talking about. You're talking about something that can take on as big a number as it can, negative number, non-integer. Okay? Make up your mind first. Make up your mind. Okay? And if it's univariate, these are the choices. If it's multivariate, the choice is a little bit less so. But anyway, so these are the most common. There are more than this. Okay? Obviously, Wikipedia, they cannot list them all. If you want exhaustive list, you have to go to Mathematica. But let's say this, by the time you exhaust this list, nobody wants to talk to you anymore. You're too much of a nerd. Okay? And I tell my student, and I tell Basai student, there are actually 10 names in here that you need to know. The rest of them you can ignore. And you will survive the rest of your life. You will not run into any problem unless you go into something specific. For example, if you're going to insurance mathematics, there'll be a kind of like a niche distribution. You go to like economic equilibrium, maybe there's a, if you go to engineering reliability, there's a kind of like a niche distribution. But for a part-time student, there's no more than 10 names in here that you need to know. Okay? Just for completeness, I'll tell you what they are. Bernoulli, which you don't know, or you don't need to know if you know binomial. So I'm going to say, if you know binomial, okay, binomial, Poisson, it's 2, right? Beta, 3. Gamma, it's gamma. Gamma, 4. Normal, 5. Student, 3. T, 6. Okay. And then there are about 3 or 4 more that's good to know, like exponential, blah, blah, blah. So in here, there are actually about, you don't need to, but the good news is you don't need to know more than 10 that way, okay? Because there is enough degree of flexibility. Look at that beta, right? Just by tweaking alpha and beta alone, you get so many shapes. That's what modeling mathematics is all about. Choose the class of function. That class of function allows you freedom to turn the knob. Choose the function wisely, then tweak the knob nicely. That's your job at the moment. Okay? Now, that's it. That's probability. What is statistics? Statistic is the opposite end of this. Statistic is already not asking what the probability of something that has happened. Statistic is about things already happened. Yeah? So to have statistics on rainfall, it has already rained. And somebody wrote down how often it rained in Bangkok during the month of August over the past 100 years. Statistics is about real events recorded. But in this case, the reason it ties in with probability is because, well, we probably have done this in Excel, right? Get the data into a histogram. Basically, okay, and this is the bottom line. Statistical analysis is about getting your data, plotting a histogram, and ask yourself, which amongst the mathematical functions, the 10 functions that I told you that you have to memorize, which one would you choose to fit the histogram? So you have to choose wisely. If the histogram covers non-negative value, only positive value, right? And you use normal distribution, and you do a good job. No, because you can use something that can be negative. So you're not wise, right? So take the data, do the histogram, choose the right function, and then tweak the parameter so that it fits nicely. That's it. That's it. Once you did that, you consider yourself learn from the data, right? Because you can't do it more. I take all the 100 years of rainfall and I put on a histogram. Okay? And based on that, I choose the best function that I can find in the Wikipedia page, in Mathematica, in Python, in R, I don't care. And I choose the parameter, tweaks it so that it fits the histogram so nice. It doesn't fit any better than this. Once I've done that, I show the data. Okay? I show the data. Well, not really. Now, here is where I want to tell you something about really not fun. Something very serious. statisticians, you think that statisticians like each other a lot. Actually, there are two kinds of statisticians. They don't get along. Okay, like Andy and Nancy. One class is what's called classical statistician. These are the guys who did exactly what I told you. Get the data, fit it, and that is done. Okay. If you're going to redo this, you have to redo the whole thing. Okay, you have to redo the whole thing. Maybe you have more data. Fine, add more data. Rerun the whole thing. Okay, so you have to build a building, and if you want to modify it, you rebuild it from scratch. Okay, because data represents reality. All data represents all you know about reality. Then along came base of priest. I don't know if he's Catholic. English statistic, Presbyterian. Okay, Presbyterian, Bay. He's very clever. In fact, he's saying, even without data, I'm just going to guess. I'm just going to win. So, before any data, he already has in mind the distribution. But if you give him data, he will keep tweaking. So he doesn't throw anything away. So even no data, he already got the curve. Give him data, he adjusts the curve to reflect the data. Give him 1,000 pieces, 1,000 data points, it's not very good. Tomorrow you come up with 5,000, he doesn't redo the whole thing. Okay, it's very stingy. Well, okay, have 5,000 more data, give it to me, I'm going to tweak the curve. And just keep adjusting. Okay, this was considered nasty work by classical statisticians. So classical statisticians and Bayesian statisticians didn't get along. Okay? There were no murder or anything like that. Certainly there were heated arguments. But the funny thing is, and I've always been a Bayesian at heart, nowadays, because of neural network, the transfer learning, the kind of deep learning, everybody is a Bayesian. Keep on adding more data. Big data is all about that. You have small data, you can do better with bigger data. You don't throw away anything. So nowadays, practically, in spirit, everybody's a Bayesian. So when I was your age, Bayesian was like straight statistic. Nobody talks to people. One tenth of statisticians do Bayesian or something like that. But now everybody's a Bayesian by default, by nature. Okay. So that's just a funny story I want to tell you. So Presbyterian minister who's known for, and his formula, basically, you only need to know one thing. Because he can keep adjusting, the probability function to start with is called prior means before you get the data. You add more data, you update it in a posterior distribution after. And that after becomes prior for the next data set. But you never finish. Keep improving. Okay? It's like, I don't know, in Thailand, street food is very popular. And you can always go to the noodle shop where they have this pot of beef noodles. They've never been washed 50 years. Right? Just add more soup, add more beef. Okay, that's a basic noodle. Okay, no starting from scratch. Okay, so this is how done. So there's a prior, and the way it's written. This is very clever. You never think of this. Whereas classical statistics thinks of a distribution, and that's a parameter, right? Now, classical statistician thinks that God has made up his mind or her mind what F is, what theta is. Theta is fixed. Okay, it's in the mind of God. You get the data, so you guess what the right alpha data based on the data. Bayesian is different. Bayesian is like this. Bayesian is saying, I have a prior data. Yeah. Then based on this, somebody gives me data. I have posterior. So it's not value given the distribution parameter. The parameter is given the data. And then you keep doing this forever. Then you just have this. So P1, P2, and then a P3 is data. Third version, second version, even more X. Keep doing this, and go forever. So that's probably basic. Now, in reality, there's one form of decision probability model that you call Bayes 3. And this is where you start to do something like, well, let's do this. What's the probability that this guy is has a COVID, right? So everybody has a baseline probability of COVID. That's higher. Okay. You call. By the way, the probability has just gone up. I updated my model. Yeah. You can't taste any good food. I update my model. That's how basic works. And this is how neural network works. So I have done something that is rarely ever done, which you actually put literally Bayesian statistic in the framework as machine learning. And it fits it that nicely, except most people don't know both against it too. Okay, so probability statistics. Now, before I go on, and we're gonna take a break in 5 minutes. Before I go on, let me just give you the classical statistician way of work, how they work from. This kind of work from. They assume that God will tell them to use a F. Their job is to find failure using the data. So there are two problems that they work. One is called estimation. Okay? So this is not how they think, but this is how they work. Estimation is this. I'm going to assume F of X given data. Then I'm going to get the data. I need histogram, and that's going to give me my estimate. Put this hat. You guys see this Japanese hat? Yeah. So this is an estimate of this. The whole statistic theory is to say that this thing gets closer and closer the bigger the sample size. Okay. Remember, they can only do it once. They have to throw everything away. So these are the guys who they want the big data set right away. Until you get the big data set, they can't really do it. Okay. So this is their whole world. That's one. The other one, the other way of this thing is called hypothesis testing. Hypothesis testing is it's like this, except instead of estimating this, somebody gave an estimate. And they test how believable it is. This is called estimation problem. That's that. And the other one is called hypothesis testing. Now, hypothesis testing is important. Okay? Again, I pick and choose everything I learn because I know it matters. Even though I'm not a Bayesian, I use machine learning. There's one element of classical statistics you need to master, and that's called hypothesis testing. Not any kind of hypothesis testing, but general. That hypothesis testing goes something like this. Now hypothesis. This thing is equal to 7. Okay? H alternative. Okay. In reality, it could be 0, whatever. The point is that null hypothesis is something specific. Alternative hypothesis is not that. Okay. How many values can specific theta be? One value, theta is 7. Okay. But when I say alternative hypothesis, A is for alternative. Usually this is called 0, like not. You think now. Okay. A. Now, wait. How much bigger? Okay, something like that. Now let's look at this picture. Okay. And this is what they're going to say. Under this hypothesis, a test statistic could be mean, be something. We have this distribution. Not the distribution of the original problem. It's a problem is a distribution of some test. Okay, and this is always called test statistic. Yeah, I'm telling you something that's very generic. Okay, test statistic. Under this is distribution. The whole point of having a data is to get the test statistic from data. And if the test statistic data points to here, what do you think is going to be the conclusion? Okay, this is probability function, the probability of the test statistic. Okay, think generic. So it should be somewhere close to 0, right? Okay, under some specific statement, it should be like this. So if you find something like this, you have to kind of accept. But if you have something that shows up here, or you start to get uneasy, right? You get something like here. Why is it out there? It should be close to 0. Okay? It's always going to look like this. Okay? Under something specific, it should be close to 0. But it's so far out. How far out? This area here is called the p-value. Sometimes you say 1 minus that. But yeah, I'm going to say that's that. Yeah. But again, sometimes it's 1 minus. The point is that if this is so tiny, I'm just going to doubt this guy. So the whole job is to say, based on the data, the test statistic is here. Under null hypothesis, it should be kind of here. The reason it's so far out, how far out? There's only like 0.1% of the area to the right. So it says something like this, it's less than 5% or 1% or something like that. I'm going to say, nah, I don't believe it. I reject. Reject in favor of this. And that's very important. Classical statisticians are very nitpicky. They have to say, I reject this. I don't accept it. Okay? They don't accept anything. They can only reject this in favor of this. But they're not going to say what this is, because this is actually not specific, right? Greater than 7, 9, 10, 11, 12. The point is, if theta is going to be 7, you would expect to see things around here. But you see things around here. Unlikely. That's called failing test. And that test can be framed to mean anything. Can be framed to say something like, oh, this election is not a fraud. Oh, the rainfall is normally distributed. Oh, the height of a person is a function of the height of, it can be any kind of statement. The job, professional statistician turns every problem you want and the two to get into the form of this. Get all the data into the form of this. And if you get this, you say no. The job is to be able to say no without doubt. Okay? But they don't say yes to anything. Okay? So this is going to happen. Now, why? Why do I, again, I'm not a classical statistician. Why do I bother with this? Because even when you go to machine learning, when you test whether or not the model is good, it's going to be something like this. Good. And under good, you're going to get this distribution with the test statistic. And if you get something that's here, and you get something that's here. If it's out here, and yeah, or it could be any kind of statement. The point is that this way of spreading things is going to stay with you, even if you're not using statistics ever. You're not a buyer of classical statistics as neither am I. I'm not a classical, but this is how there will be a, I just give you the word, non-parametric test goodness in your model. That is always going to be. Okay, so even if you go to deep neural network that attacks probability Bayesian or non-Bayesian normal distribution in 100 yards. Okay, nothing to do with statistician. There's going to be in the final analysis some kind of jump. Like, is the model good? Goodness of fit. And that goodness of fit will be proved by some kind of test statistic. And if that test statistic is way out, it didn't do a good job. Okay, so that's why even if machine learning will have, that's why I think so. For the past hour and a half, I basically went through the thing that will be the foundation for the rest of the book. I'm going to let it go live.